Hey, here we are doing another Toolbox, stunt rigging Toolbox talk. I gotta say, I'm sitting down today because I've cut this thing 6 times so far. It's just a pain in the ass. There's too much info and I go down the rabbit hole. As you all know, I tend to do that anyway. And the situation now is, what is too much information? This Toolbox talk is going to be backpedaling to a bunch of break videos we did, numbers, I don't know, 5, 6, 10 through 20 or whatever, where we broke eye to eyes, we broke eyes over thimbles, eyes without thimbles over shackles. We broke a lot of line. And this is primarily about the line, not about the Delta Maillon or Maillon Rapide, because those broke at what they were supposed to. It's mostly the rope I'm issuing right now, or the issue I'm dealing with. So that's what this one is about. We're going back to Samson Tech 12 and the strength of Samson Tech 12. Because currently, preface, we did a ton of these videos and we used crane scales, digital crane scales, which achieved the purpose. We got numbers. We were able to get tests done. The problem is in sample rate. And what started the whole problem actually was we kept destroying our 5 and 10 ton crane scales, because when the line breaks, what happens is it doesn't hurt the scale because it's a big block of aluminum with a load cell in it, but it also has the electronics in it, and that sharp vibration, that heavy oscillation that goes through it, was starting to kill load cells. So the digital readouts, because they're on the actual device, were taking a shit. So we ruined several, they're a couple grand a piece, and we ruined several of them. So that was an expensive lesson. So in between all the other projects last time, what I did was I bought a Z-beam load cell that has a computer attachment. So all of the digital bullshit is here on the computer with the interface, which is in this magic little box that goes to the computer. So what now I do is I read all this shit out here, and it's cool because I get graphs. I can do step over graphs. I can lay one graph on the other. I get all of the numbers in the world. And the Z-beam that's actually sending the resistance, the frequencies to this, is pretty much bulletproof over there on the dyno. And this is our 12-ton dyno we built a couple years ago. And what I did was I went for a 5-ton load cell because the resolution is going to be better when breaking rope like 6 mil. Now, if I get fat and happy, I may buy a 10-ton one of these, or a 15 or 20-ton for when I do big shit. But the fact is, the max on this is 12-ton. So a 10-ton load cell would be fine. I'd hate to turn this thing into a pretzel. It's a giant I-beam. It would be very messy. It's bad enough breaking small shit when it flies, but this could be ugly. So right now we're just dealing with the small shit, bollards, gold tails, which gold tails we did on the old system, and we were able to go to, over 6 ton. This will only register to 5 and some change. So that's kind of our borderline, but we've already done enough research on those. So for all the normal flying, performer flying stuff, this is pretty much how it's going to be. What we've got, the reason I'm doing this all, so now I've got this system, and it's really cool. The issue is it samples 1,000 times per second. Now, if you remember back to all our data, I was relatively pissed, and I couldn't figure out why we were running numbers well below manufacturer spec. Now, 12 millimeter Tech 12 from Samson, which is 6 millimeter Tech 12 from Samson, which is 1/4 inch, which is actually 6.43 millimeter. It's a little bigger. The average strength is supposed to be 3,700 kilo, or 3.7 tons. The minimum strength is 3,300 kilo, or 3.3 tons. And these are both figures in the spliced configuration, okay? And we weren't getting anything close to that. We were fucking 1,000 kilos under that. We were 1,000 kilos under that, okay? Which is an important number to remember because it'll become clear to you. So that's in spliced condition, 3733. The iso strength, unspliced, just wrapping it on both ends of a drum and trying to break it, is 3.7. So we were looking at those numbers and we were getting 2.2 in spliced, 2.3 in spliced, and we were getting, that was our average. We weren't getting the 3 minimum. We were 1,000 below. Okay, so I could never figure it out, and I just figured it was because of the black magic voodoo that big dollar companies like Samson have. They use giant drums, they go super slow, the radius is not a problem, because we've proven the radius is an issue, we've proven the dynamic speed is an issue, we've proven all that with the lesser signaling dynos. Now, here's where it gets interesting. The average crane dyno will sample between 2 and 200 times a second. Most dynos, like the Dillons or the Kerns, they sample 10 times per second. Kerns are 5 times per second, okay? So what we now have is if it's a Dillon, it's 10 times per second, and we now have 1,000. We have 100 times that, 1,000 times a second. If it's a Kern, which is 5 times a second, we now have 1,000, which, as you know, is going to be 500 times. You know, so I'll do the math later, but you get the picture. You know, the tens are easy to work on. I'm not going to do the math here. Anyway, so, and the really expensive crane scales will go up to 200 per second, but you have to understand, put that decimal term. That's 0.02 in time. 0.02 is what it samples. Now, this also gets complicated because the resolution to the digital output, which is what I was reading all the time, is sometimes updates every 2 seconds, okay? So if the digital display updates every 2 seconds and they're sampling and something's breaking in the time frame between its sample rate, its update rate, you're only gonna get the last update on the last number. You're not gonna get the newest. So what you have is a gap, big gaps. And what we found is that tech, because of its lack of stretch, operates in hyperspeed when it comes to braking, okay? So it breaks, it goes from 300 to broken in under load in, let me look at some numbers here. 300 to broken in 1.3 seconds if you just run it straight through on this. And the numbers just go, because we always bring it up to tension first. I don't try to slam it into a slack. So we bring it up to tension between 2 and 300 kilos. It's usually closer to 300, 250, 300. It's by eye. And I look at the graph. And from that point, a straight test. Hit the button and watch it rock. It takes 1.2, 1.1, 1.3 seconds to breakage. Okay? So look at your sample rate on a crane scale and look at the sample rate here. So if you want to look, I'll put up the graph now so we can continue this discussion and you can see it. But per unit time, it accelerates extremely fast to brake. So the timeline, if here's your graph, the timeline on the bottom is very short and the forces generated are extremely quick. So it goes from, in multiple cases, 257 to 3485 in 1.3 seconds. Another one was similar numbers, and these were our lowest braking numbers. We're in the 3400s, and these were all on straight poles. So you can look at this graph. I'm going to splice in now. I'm getting smart in doing this because I'm trying to bop back and forth in the edit is fucked. I hate doing the edit. So I'm going to give it a break. You can look at the graph. I'm going to put up the straight through graph and the straight through brake test. So resting in the 2 to 300 range up to breakage, which is just hit the button, straight pull, okay? And then we'll come back and we'll go from there. Okay, so you've looked at that graph, and now you see what I'm talking about. It, we got timestamps on these things that go to 4 digits. So when I'm looking at timing, it gives me seconds, so up to 60 seconds, but the numbers and then 4 decimal places afterward. And I wanted to try to extend this breakage time because it's just so short on a straight pull. And our lowest numbers, now they say, Samson says 3,300, so 3.3 tons, kilos, is the minimum strength. We're getting over Samson's minimum every time, but it's for a nano blip. It's literally zero point 0.1 of a second, 0.12, 0.14 of a second that you see it takes for it to go from that number to breakage. Now, I needed to clarify this. So what we did was I tried going up in steps. Okay, so I would take it up from 3 to 5 to 8 to 12 to 15 to 2 to 2.2. And on some of them, I was lucky enough to take them up all the way to 3.64 tons in tension with a stop. And then go from there to break it. And that was a nano blip. That was less than 1/10 of a second. And it broke at 38.65. There's also something interesting. So what happens is, I'll post these now, I'll break into it and we'll look at it. But by taking it up in steps, at the lower end of the spectrum, between 0 and about 1,000 kilos, about a ton, as you go up in a step, it doesn't lose much tension because it has stretch up to 30% of its, up to 1.6% stretch, up to 30% of its braking strength. So in that first up to a ton, as you go up, it's a flat line on the step. And I was giving it sometimes 3 to 5 seconds, depending on my patience level in steps. And you'll see that on the graph. And I went up in increments. And once we started getting up around 2.5 tons, 2,350, 2,400, what happens is the stretch causes it to go slack more. So at the lower end, the resting period, it loses 100 kilos. Once we're at this much tension, 2.5 tons, you're losing 300 or 400 kilos from the peak when I'm on the button to where I let it rest in those 5 seconds. It will drop 300 to 400 kilos. Now, I know this is not moving. I know nothing is changing here. This is a 12-ton cylinder, so 2.5 tons isn't going to change it. But what you have is the rope adjusting and stretching and settling. It's not just climbing. So it hits a point, it comes down 300 kilos, and then I bump it to the next level. So you'll see that on the steps. And then after you look at those, I'll come in and discuss that again. All right? So now you've seen the steps, and you've seen the last step I had was at 3,646.5 kilos. And from there, it was less than 0.1 of a blink of an eye till it skied at 38 and some change and broke. So, and it had lost almost 400 kilos in its last 5-second rest at 3.5 tons, 3.6, to break at 3.8, but it only took literally touching the button and it went off again, it broke. So by looking at that, we can infer a couple things. A, the stretch rate. We take all the stretch out, and then there's nowhere for it to go, so it keeps trying to stretch. So you're elongating this rope. So it will continue to stretch, and you'll lose more weight at the high end of the scale than you will at the low end of the scale. But conversely, when you reload it, you have faster climb than you do at lower because there's less room to go. So from each step, it's a shorter distance to climb more. So as you load this more, it takes less unit per time to destroy the rope. Okay? So that's where we're at now on this. You've got a couple of samples of straight through on the button, stepped, and you'll have to realize that all of this is braking strength, and it brings up a couple of points. One, really happy we're getting the same braking strength as Samson calls out. It's amazing. It's great. I mean, I understand it, and it's like not a lack of knowledge, but a lack of information and equipment cost, because these things ain't cheap. And now with the added information, I can see what the problems were on the other, the first 50 we did versus now. Also, you have to understand that the sample rate on the old dynos contributed to that problem in our understanding of the maximal braking strength. Now, does it change our ability in terms of design factor, or if you want to call it safety factor? Well, that's a good question, because normal working loads for rope are between 15 and 25% of the MBS, okay? So you go out with whatever climbing rope and you're gonna work in the 15 to 25% range. You go out with a piece of tech and they give you specs up to 30%, so that's 1.3 tons. If it's breaking at 3.8, call it 1.25 tons. Okay, so that's 30%. At 1.25 tons on a 6 mil rope, you're getting 1.6% stretch, but you're at a technical 3-to-1 design factor over the MBS, or the high side of the it's 1.1 tons, over 3.3 MBS, minimum braking. Now, the normal average braking is 7 and 8, 3.7, 3.8. Okay, but let's calculate it off the MBS, the minimum number. It's 1.1 tons is your working range. Okay, if you go by 30%, which is high based on most rope standards, because fiber ropes sometimes go derated at 1/6 of their braking rate. And these are all static applications in 20 to 30% braking, derating for a design factor. So now once you start talking about dynamic loads, thinking of it, again, put it in our terms, a gold tail drop with a 100 kilo body doing a big hero gold tail drop is going to generate 5 times the body weight. So if it's 100 kilos, you're generating 500 kilos of force. Now that is 50% of the working load if you're at 3-to-1 based on the MBS. If 3.3 tons divided by 3, 1.1 ton, 1.1 ton divided by 500 kilos, 50%, boom. So you are at only a 2-to-1 on your working load right there. Now, on your overall braking, it's one thing, but on your working, you're already half of your working load. So any other things that create stresses on this, i.e. a rope gets an asshole and gets stuck in the gold tail, a sudden stop, a sudden anything, all of a sudden you're generating far more forces. And you can do this and calculate this with negative acceleration formulas on dropping objects and stopping them. So you'll know the speed they're traveling, their weight, and then you can calculate how hard they're going to hit, like you do for factor 2, factor 3 falls, things like that. So all of this plays in when you're using the rope. So the question gets to be is, on the MBS, now I can believe the MBS. And before I was only worried about working rate. Because basically I accepted what was on the dyno at a spliced of 2.2, and since the shackles broke before that, and since the eyes were breaking at that, I pretty much knew that was my max. But I always wondered what the real MBS was. So now we're able to get the MBS and realize that our working range is actually less than we'd thought, because of the speed with which it accelerates breakage over time, meaning it doesn't take a shitload to go from 2 tons to 3,800 in terms of pull force, in terms of how quickly it accelerates, meaning it's got zero stretch left in it. And it's not able to absorb anything, especially we're talking dynamic loading. Hence why they tell you not to use this kind of rope for dynamic loading, but we do, and that's the reality of it. So now you've seen the graphs, now you know the numbers, and the basic realities of rope safety, 25% of the braking strength. So if your braking is 3.4 minimum, 3.3 minimum, you take a quarter of that. Okay, if you want to go to 3 times, if you want to go 1 more, you can. But you're looking at a working maximum loading on that rope of basically a ton. Okay, to allow for anything else. Because from 2 tons to 3,800 is 0.12 seconds, 0.13 seconds, 0.15 seconds. It's just absurd how quickly that happens. Okay? So, and even when you have the capabilities to go from 300 kilos to 3,800 kilos, it takes 1.3 seconds. Okay, and that's fairly dynamic because of the speed with which this ram moves. I'd have to go back and look at the initial, but this strokes out in about 10 seconds to go a meter. So it's about 100 millimeters a second, which once you get to this rope and trying to stretch it in this time span, there's not that much left in it once it's up to stretch. You've got this 4 inches, 100 millimeters, depends on what country you're in. That's a huge distance when the rope's only, is generating massive force per millimeter of distance. It goes up so quickly, and you've seen it on the graphs. So that's all I wanted to go through and bring some thoughts into is how you get your safety ratings or your design factors on something like this. Because remember, MBS doesn't tell us the story. I mean, I'm breaking these. This is a 53 kilonewton carabiner, and I was breaking stuff eyes to eyes. And at 3,800, it was destroying the carabiner. It tried to open the gate at the nose because this was flexing on the spine and bowing it open, and the nose basically took a chunk out of the gate because it was trying to keep the nose closed. And instead it ate the carabiner, and that's 5.3 tons. That's, a 53 kilonewton beater that's supposed to hold it. I have a 75 kilonewton carabiner on the other side, and it didn't budge. But at almost its top load, this was not a happy camper. So this one's now in the trash. Yet more equipment in the trash. So MBS doesn't, this is where it gets tricky for everyone. MBS versus working load. And we need to, as professionals in this field of stunt rigging, need to go for working load. We can't be relying on braking because of this type of situation. Per unit time, the forces generated are so accelerated, there is no coming back from them. Okay? And that gets to be a huge issue. So, like I said, even if you consider loading 30%, think of a situation where you've got, we do it all the time. We do tight slack lines or what I call loose tight lines. You do a high line that's not loaded to, say it's loaded to a ton. And you've got somebody rolling back and forth on it because it turns into a track in the sky. Well, that's great. But you put a 100 kilo load on that catenary line, and all it needs to do is a bit more activity, and that 100 kilo load on that 1 ton load, now you're skying well over 2 tons. And you could do the math. I've got catenary formulas and they're available online. And you'll see it. Forget the anchors, because say you've got your anchors covered. Okay, you've got your 2 redirect pulleys taken to the ground. You've got unlimited weight here. It doesn't matter. So from here to here is no issue. It's the pulleys, the force generated on whatever they're hanging on, and the force that exists in the line. And you'll find that it's exponential. So you can quickly, very, very quickly exceed any type of braking strength on this rope if you don't pay attention. Okay, so these are the limitations of the line we deal with, at least in 6 mil. Of course, you can go to 8, you can go to 10, you can go to 12. It all depends on what you want to do, but you got to know firsthand. And I've seen a lot of guys just string it up with 6 mil, and especially on a set where they figure, oh, it's not that much, and it's indoors. We're not doing outdoor super high lines between cranes. We're just doing stuff from the reds that are going through a set and redirecting it, and then putting it to ballast and ground anchors and calling it good. You really are exceeding the levels of the rope. You are down to less than a factor of 1 on your 50%. You're less than 50%. You're approaching limits of braking right there. So you got to think about these things, and it's great to have this new tool. Like I said, sometimes it's too much information, but I wanted to go through it with you and intercut the graphs, and you'll see. So, I'm not going to go back and break everything all over again, because I already know the limiting factor on Wichard shackles or Maillon Rapide, or Mallions as they call them in England. Maillon Rapides. We already know the Delta Maillon. We already know all of these factors. We know what their limiting factors are. We know they're going to hold more than the rope, and we've used bigger rope to prove it than 6 mil. But since 6 mil is our normal common line in stunt rigging, I just wanted to go through these things with you. Just remember, it's working load. It's not minimum braking strength. But on the flip side, I said we're happy. We are now on to sampling instead of between 2 and 200 times a second, which is a wish list, to 1,000 times a second. And we can radically see the difference as we progress through force. And that's our happy news for today. We try to keep things always learning. I mean, it's great. I could afford to get one of these and learn how to deal with the program. And I just had it recalibrated because the first time I tried it months ago was a complete clusterfuck because it wasn't measuring in units I could relate to. And I couldn't change it because I'm not real competent on Intel style computers, which I had to get this unit and load this onto it because this is its only designated task in life, is to do this. I have ones for tuning my motorcycles that their only task in life, because it all somehow runs off the Intel and off the Windows and off the engineering style computers instead of Apple computers, which I use. So this one's dedicated job is this. But now you know your line strength. We already know where we're at breaking the shackles and breaking Maillon and breaking other stuff. So you can just put all of that in the jumbo mixer of how you want to assume your risk in design factor. Because that's what it comes down to. So, I mean, you can get away with pushing the edge and not, as long as shit doesn't break, you've succeeded at least once. But in terms of regular design of rigs and regular design of ways to operate and regular design of safety protocol, these kind of things come in really handy. So we've been really busy here in the shop. Just as a side note, we've been building some new ratchet trigger boxes for customers, finished them, but of course it's always a pain because certain parts aren't available anymore and we have to go through and get substitutions and then redesign around the substitutions. Nothing critical like the valves, but like gauge size, pressure gauges, shit like that. So the panels need to be recut for the correct size, or I have extra panels. You got to make bezels for everything so it fits correctly. Just little shit like that. We've been building bollards because, again, this kind of information, we know that circus ties only hold 1 ton, period. That's it, Even with this machine, I did some testing on them and I got up to 1.3 on some of the lucky ones. But that's MBS. That's not even working load, kids. So when you're thinking of we're just going to do this and wrap it around a carabiner and hook it onto your ratchet or hook it onto your whatever engine of choices for motivation, you're only working at 1 ton, period, braking. You're not working at working load 1 ton. So you've taken a 3.3 minimum braking strength rope and now are using it to where it's braking at 1 ton, and now you have to take the design factor on that. So even at 50%, that means your max loading is 500 kilos, period. That's it. That's a 2-to-1. So these are all issues, and the bollards are bringing that into play because when you tie shit around a carabiner and you exceed the 1 ton, it fucks the rope. So what's the point in having 20 meters of rope tied up in a hank attached to that? Well, if I need to move it here, I need to move it there, I've got extra rope. How about you just put a service loop in? Perms are 6 meters minimum, sometimes much higher. Float the bite halfway up. Now you can take, say it's a 12 meter perms. You can adjust 6 meters farther away or 6 meters back without ever touching your operating marks. And you can move your performer around wherever they need to go, and your rope stays intact and there's no wad of shit flying in the air. For those wad of shit flyers that like to leave the extra, you'd have to know that your carabiner wrap, whether it's the tiger tie or the this circus tie or the that fucking tie, where you just are wrapping shit around a carabiner and throwing a bunch of bites behind it and looping it off into the carabiner, well, you're braking on that as 1 ton. Do with it as you want. I mean, for a hand pull, yeah, you're not going to generate more than a ton, but that's your braking. It's not even your design factor. So you've taken a rope that's, normally you operate at 1 ton at a 3-to-1 design factor. You're now at a 1 ton braking strength. And, if you're going to be optimal, it's going to be derated to 500 kilos. Well, that's not a fucking lot. You can generate 500 kilos pretty quick. So we made these so that you don't have to tie, for the wad of shit users, you don't have to tie them. And these are currently breaking it on the new dyno at 2.2 tons or more. But the point of these is so you don't destroy the rope, because if you've wrapped it over a 12 mil carabiner and it's pulled almost to a ton, you fucked your rope. So it doesn't matter if you need to let out 10 meters or bring it in, your chunk of rope's fucked, especially on the let out, because now you have damaged rope in the system. So the point here is to determine where the rope damage occurs, and we're working on that. Just a side note on general housekeeping. Since I'm not doing as many of these because I've been busy and they don't generate any income and they cost me a shitload of time and money to fuck around with this stuff, I got to play with the new toy, and I thought I'd bring you into the loop on the new information. So that's it for now. Just food for thought on braking strength, MBS, versus working load limits, and backpedaling on the Samson Tech 12 6mm. We are now happy to announce we're getting manufacturer's specs, so I don't feel bad. All my splices hold, and it's a beautiful thing. They're breaking in the eye, meaning the eye is rupturing. We've only had 25-30% are in the eye, 20% are at the Brummel crossover, and the rest are actually in the middle of the line between the two tails. We've had no tail breakage at all. So my splices don't break at the tapers. They break at the crossover and in the middle where it's over the radius of either the carabiner or the shackle or whatever it is. Those are what we've had. Out of the wad of them, we went and rebroke again. So just all more information to put in the giant blender to make decisions for rigs you're doing. All right? Take care. We'll talk to you soon. Stay safe.